The following is a conversation with Clara Sousa-Silva, a quantum astrochemist at Harvard, specializing in spectroscopy of gases that serve as possible signs of life on other planets, most especially the gas phosphine. She was a co-author of the paper that in 2020 found that there is phosphine in the atmosphere of Venus, and thus possible extraterrestrial life that lives in its atmosphere. The detection of phosphine was challenged, reaffirmed, and is now still under active research. Quick mention of our sponsors: Onnit, Grammarly, Blinkist, and Indeed. Check them out in the description to support this podcast. As a side note, let me say that I think the search for life on other planets is one of the most important endeavors in science. If we find extraterrestrial life and study it, we may find insights into the mechanisms that originated life here on Earth, and more than life, the mechanisms that originated intelligence and consciousness. If we understand these mechanisms, we can build them. But more than this, the discovery of life on other planets means that our galaxy and our universe is teeming with life. This is humbling and terrifying, but it is also exciting. We humans are natural explorers. For most of our history, we explored the surface of the Earth and the contents of our minds. But now, with spacefaring vessels, we have a chance to explore life beyond Earth, their physics, their biology, and perhaps the contents of their minds. Now is the part of the program where I do a few minutes of ads, and never any ads in the middle. I think those are annoying and really get in the way of the conversation. I try to make these ads interesting, but I give you timestamps, so if you skip, and I hope you don't, but if you do, please still check out the sponsors by clicking the links in the description. It's the best way to support this podcast. I'm fortunate to be able to be very selective with the sponsors we take on, so hopefully if you buy their stuff, you'll find value in it just as I have. This episode is sponsored by Onnit, nutrition, supplement, and fitness company. They make Alpha Brain, which is a nootropic that helps support memory, mental speed, and focus. I've recently been using it on occasion to be a kind of super boost when I'm thinking through a difficult problem. It clears the mind, helps me maintain focus. It's really important for me to not rely on anything like that, so I don't take it as a regular part of my productive life. I take it as a way to boost my mind through difficult, deep work sessions. Plus, I really like the brand Onnit. I get to pass their gym quite often while I'm here in Austin. Obviously, Joe Rogan is involved with it, and since I've been a long-time fan of his podcast, the Onnit brand is kind of implanted in my head at this point. Anyway, go to lexfriedman.com/Onnit to get up to 10% off Alpha Brain. That's lexfriedman.com/Onnit. This show is sponsored by Grammarly, a writing assistant tool that checks spelling, grammar, sentence structure, and readability. Grammarly Premium, that's the one you pay for, offers a bunch of extra features. My favorite is the clarity check, which helps detect rambling, overcomplicated chaos that many of us, certainly I do, can descend into. Whenever I say a sentence where parts of the sentence rhymes with another part of the sentence, my brain gets distracted and I start mentally giggling at the internal dad joke of it. I find a little bit of silliness is good for the soul. It reminds you that life is quite absurd. What does that have to do with Grammarly? I have no idea. Anyway, Grammarly is what Clippy always wanted to be. It's a kind of little assistant that guides you. You don't necessarily have to accept all the suggestions it makes. It's almost a thing you argue against as you try to clarify and improve your writing. Grammarly is available on basically any platform and major sites and apps like Gmail and Twitter and so on. Do more than just spell check. Get your point across more effectively with Grammarly Premium. Get 20% off Grammarly Premium by signing up at Grammarly.com/Lex. That's 20% off at Grammarly.com/Lex. I wonder if it can help me mumble less. Maybe there's a company called Mumberly.com, and maybe they can be a sponsor too. This episode is also sponsored by Blinkist, my favorite app for learning new things. Blinkist takes the key ideas from thousands of nonfiction books and condenses them down into just 15 minutes that you can read or listen to. There's a huge number of really popular books on there, many of which I would recommend, like Sapiens or Homo Deus by Yuval Harari. I've been thinking of doing a project where I read a book a day for maybe like a month. since I've been really slacking on the amount of reading I'm doing per day. It's really been in like 10 minutes, 20-minute periods, as opposed to hour, 2 hour, 3 hour, 4 hour. I want to get back into sort of serious reading, note taking, and thinking through stuff. I think it makes me a better person. I think it makes me a better friend. It makes me a better conversationalist on a podcast, certainly. Makes me a better mind that thinks about this world. Reading is like the most efficient and cheap way to travel, both through space and time. So I definitely want to do that kind of project. And Blinkist helps me guide which books I want to read or which books I want to reread. It also reminds me of the key ideas from books I've already read. It's just a great companion to the full reading experience. Go to Blinkist.com/Lex to start your free 7-day trial and get 25% off of a Blinkist premium membership. That's Blinkist.com/Lex, spelled Blinkist, Blinkist.com/Lex. This episode is also brought to you by Indeed, a hiring website. I've used them as part of many hiring efforts I've done for the teams I've led. They have tools like Indeed Instant Match, giving you quality candidates whose resumes on Indeed fit your job description immediately. Actually, as we speak, I've been doing interviews with video editors today, and I'm going to do some more tomorrow. It's really incredible how many people applied to work with me and how cool they are, and just how fortunate I am to be surrounded by cool people, but also for more cool people to reach out to me and just want to connect with me. I don't know. I'm deeply grateful for that. But finding the right people that kind of have that energy, that positive energy that you can feed off of as you collaborate, as you brainstorm about how to present stuff the best way, that's difficult. But I think I'm going to be able to do it. There's a bunch of cool people in the pipeline that I'll get a chance to talk to. But hiring is really difficult, really important, and tools like Indeed make it easier. So you should definitely use it if that's what you're interested in doing. Anyway, right now, get a free $75 sponsored job credit to upgrade your job post at Indeed.com/Lex. Get it at Indeed.com/Lex. Terms and conditions apply. Offer valid through June 30th. Again, the website is Indeed.com/Lex. This is the Lex Friedman Podcast, and here's my conversation with Clara Sousa-Silva. Since you're the world expert in, in many things, but one of them is phosphine, would it technically be correct to call you the queen of phosphine?
I go for Dr. Phosphine. Queen is an inherited title, I feel.
But you still rule by love and power, but while having the doctor title.
Yeah,
I got
kindness.
it. Kindness. In September 2020, you co-authored a paper announcing possible presence of phosphine in the atmosphere of Venus, and that it may be a signature of extraterrestrial life.
Big maybe. There
was some pushback, of course, from the scientific community that followed, friendly, loving pushback. Then in January, another paper from University of Wisconsin, I believe, confirmed the finding. So where do we stand in this saga, in this mystery of what the heck is going on Venus in terms of phosphine and in terms of aliens?
Okay, let's try to break it down.
Okay.
The short answer is we don't know. I think you and the rest of the public are now witnessing a pretty exciting discovery, but as it evolves, as it unfolds, we did not wait until we had years of data from 10 different instruments across several layers of the atmosphere. We waited until we had 2 telescopes with independent data months apart. But still, the data is weak. It's noisy. It's delicate. It's very much at the edge of instrument sensitivity. And so we still don't even know if it is phosphine. We don't even really know if the signal is real. People still disagree about that. And I think at the more philosophical end of how this happened, I think it is a distinction, and myself and other co-authors were talking about this. It's a distinction between hypotheses generation and hypothesis testing. Mm-hmm. Now, hypothesis testing is something that I think is the backbone of, the scientific method. But it has a problem, which is if you're looking through very noisy data and you want to test a hypothesis, you may, by mistake, create a spurious signal. The safest, more conservative approach is hypothesis generation. You see some data and you go, what's in there? With no bias. Now, this is much safer, much more conservative. And when there's a lot of data, that's great. When there isn't, you can clean the noise and take out the signal with it. The signal with a bathwater, whatever the equivalent of the analogy would be. And so I think the healthy discourse that you described is exactly this. There are ways of processing the data, completely legitimate ways, checked by multiple people and experts, where the signal shows up and then phosphine is in the atmosphere of Venus, and some where it doesn't. And then we disagree what that signal means. If it's real, and it is unambiguously phosphine, it is very exciting because we don't know how to explain it without life. But going from there to Venusians is still a huge jump. And
Venusians. So that would be the title for the civilization, if it is a living and thriving on Venus as Venusians.
Until we know what they call themselves, that's the name, yes.
So this is the early analysis of data, or analysis of early data. It was nevertheless, you waited until the actual peer-reviewed publication to announce? Of course.
And analysis of the two different instruments months apart. So that's ALMA and JCMT, the two telescopes.
I mean, it's really exciting. What did it feel like sort of sitting on this data? Like kind of anticipating the publication and wondering, and still wondering, is it true? Like, how does it make you feel that a planet in our solar system might have phosphine in the atmosphere?
It's nuts. It's absolutely nuts.
In the best possible way.
I've been working on phosphine for over a decade.
And before it was cool.
Way before it was cool. Okay. Before anyone could spell it or heard of it. And at the time, people either didn't know what phosphine was or only knew it for being just possibly the most horrendous molecule that ever graced the Earth. And so no one was a fan. And I'd been considering looking for it because I did think it was an unusual and disgusting but very promising sign of life. I've been looking for it everywhere. I really didn't think to look in the solar system. I thought it was all pretty rough around here for life. And so I wasn't even considering the solar system at all, never mind next door, Venus. It was only the lead author of the study, Jane Greaves, who thought to look in the clouds of Venus and then reached out to me to say, I don't know phosphine, but I know it's weird. How weird is it? And the answer is very weird.
And so the telescopes were looking at, this is visual data.
That's what you mean by visual. You wouldn't see the phosphine.
Well, but I mean, it's a telescope.
It's remote.
It's remote. You're observing. You're zooming in on this particular planet. I mean, what does the sensor actually look like? How many pixels are there? What does the data kind of look like? It'd be nice to kind of build up intuition of how little data we have based on which. I mean, if you look at I've just been reading a lot about gravitational waves, and it's kind of incredible how from just very little, probably the world's most precise instrument, we can derive some very foundational ideas about our early universe. And in that same way, it's kind of incredible how much data, how much information you can get from just a few pixels. So what are we talking about here in terms of based on which this paper saw possible signs of phosphine in the atmosphere?
So phosphine, like every other molecule, has a unique spectroscopic fingerprint, meaning it rotates and it vibrates in special ways. I calculated how many of those ways it can rotate and vibrate, and it's 16.8 billion ways. What this means is that if you look at the spectrum of light, and that light has gone through phosphine gas on the other end, there should be 16.8 billion tiny marks left, indentations left in that spectrum. We found one of those on Venus, one of those 16.8 billion. So now the game is, can we find any of the other ones?
Yeah.
But they're really hard to spot. They're all in terrible places in the electromagnetic spectrum. And the instruments we use to find this one can't really find any other one. There's another one of the 16.8 billion we could find, but it would take many, many days of continuous observations, and that's not really in the cards right now.
I mean, how do you... There's all kinds of noise, first of all.
Yes.
There's all kinds of other signal.
Mm-hmm.
So how do you separate all of that out to pull out just this particular signature that's associated with phosphine?
So the data kind of looks somewhat like a wave, and a lot of that is noise, and it's a baseline. And so if you can figure out the exact shape of the wave, you can cancel that shape out, and you should be left with a straight line, and if there's something there, an absorption, so a signal. So that's what we did. We tried to find out what was this baseline shape, cleaned it out, and got the signal. That's part of the problem. If you do this wrong, you can create a signal. But that signal is at 8.904 wave numbers. And we actually have more digits than that, but I don't remember by heart. And ALMA in particular is a very, very good telescope, array of telescopes, and it can focus on exactly that frequency. And in that frequency, there are only 2 known molecules that absorb at all. So that's how we do it. We look at that exact spot where we know phosphine absorbs. The other molecule is SO2.
If there is extraterrestrial life, whether it's on Venus or on exoplanets where you looked before, how does that make you feel? How should it make us feel? Should we be scared? Should we be excited? Let's say it's not intelligent life. Let's say it's microbial life. It's is it a threat to us? Are we a threat to it? Or is it not only, but mostly a possibility to understand something fundamental, something beautiful about life in the universe?
Hard to know. You would have to bring on a poet or a philosopher on the show.
You don't feel...
I feel those things. I just don't know if those are the right things to feel. I certainly don't feel scared. I think it's rather silly to feel scared. Definitely don't touch them. Sometimes in the movies, you don't go near it. Don't interfere. Yeah. I think one of the things with Venus is because of phosphine, now there is a chance that Venus is inhabited. And in that case, we shouldn't go there. We should be very careful with messing with them, bringing our own stuff there that contaminates it. And Venus has suffered enough. If there's life there, it's probably the remains of a living planet, the very last survivors of what once was potentially a thriving world. And so I don't want our first interaction with alien life to be a massacre. So I definitely wouldn't want to go near out of a, let's say, galactic responsibility, galactic ethics. And I often think of, alien astronomers watching us and how disappointed they would be if we messed this up. So I really want to be very careful with anything that could be life. But certainly I wouldn't be scared. Humans are plenty capable of killing one another. We don't need extraterrestrial help to destroy ourselves.
Scared mostly of other humans. So,
exactly.
But this life, if there is life there, it does seem, just like you said, it would be pretty rugged. It's like the cockroaches or Chuck Norris. I don't know. It's some kind of it's something that survived through some very difficult conditions.
That doesn't mean it would handle us. It could be like War of the Worlds.
Yeah.
You come, just because you're resilient in your own planet doesn't mean you can survive another. Even our extremophiles, which are very impressive, we should all be very proud of our extremophiles, they wouldn't really make it in the Venusian clouds. So I wouldn't expect, because you're tough, even Chuck Norris tough, that you would survive on an alien planet.
And then from the scientific perspective, you don't want to pollute the data gathering process by showing up there. The observer can affect the observed. Okay.
How heartbreaking would it be if we found life on another planet and then we're like, oh, we brought it. with us. It was my sandwich.
But that's always the problem, right? And it's certainly a problem with Mars, because we visited the if there is life on Mars, or like remains of life on Mars, it's always going to be a question of like, well, maybe we planted it there.
Let's not do the same with Venus. It's harder because when we try to go to Venus, things melt very quickly.
Yeah,
and so
it's a pretty.
It's a little harder to pollute Venus. It's very good at destroying foreigners.
Yeah, well, in terms of Elon Musk and terraforming planets, Mars is stop number one, then Venus maybe after that. So can we talk about phosphine a little bit? So you mentioned it's a pretty...
Phosphine. Love phosphine.
What's your Twitter handle? It's like Dr. Phosphine,
It's Dr. Phosphine, yes. You will be surprised here. It wasn't taken already. I just grabbed it. Didn't have to buy it off anyone.
Yeah. So what is it? What's phosphine? You already mentioned it's pretty toxic and troublesome. And what and outside trouble. Sorry, that's
no. I love it. I'm going to stop calling it troublesome.
So maybe what are some things that make it interesting chemically, and why is it a good sign of life when it's present in the atmosphere, like you've described in your paper, aptly titled "Phosphine as a Biosignature Gas in Exoplanet Atmospheres"? I suppose you wrote that paper before Venus.
I did, yes. I did. And no one cared. You know, in that paper, I said something like, if we find phosphine on any terrestrial planet, can only mean life. And everyone's like, yeah, that sounds about right. Let's go. And then Venus shows up, and I was like, are you sure? I'm like, I was sure before I was sure. Now that it's right here, I'm less sure now that my claims are being tested. So phosphine is a fascinating molecule. So it's shaped like a pyramid with a phosphorus up top and then 3 hydrogens. It's actually quite a simple molecule in many ways. It's the most popular elements in the universe: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. When you add hydrogen to them, it makes quite simple, quite famous molecules. You know, you do it to oxygen, you get water. You do it to carbon, you get methane. You do it to nitrogen, you get ammonia. These are all molecules people have heard of. But you do it to phosphorus, you get phosphine. People haven't heard of phosphine because it's not really popular on Earth. We really shouldn't find it anywhere on Earth because it is extremely toxic to life. It interacts with oxygen metabolism, and everything you know and love uses oxygen metabolism. And it interacts fatally, so it kills in several very imaginative and very macabre ways. So it was used as a chemical warfare agent in the First World War and most recently by ISIS. So really bad. Most life avoids it. Even life that might not avoid it, so life that doesn't use oxygen metabolism, anaerobic life, still has to put crazy amounts of effort into making it. It's a really difficult molecule to make, thermodynamically speaking. It's really difficult to make that phosphorus want to be together with that hydrogen. So it's horrible. Everyone avoids it. When they're not avoiding it, it's extremely difficult to make. You would have to put energy in, sacrifice energy to make it. And if you did go through all that trouble and made it, it gets reacted with the radicals in the atmosphere and gets destroyed. So we shouldn't find it anywhere, and yet we do. It's this kind of weird molecule that seems to be made by life, and we don't even know why. Life clearly finds a use for it. It's not the only molecule that life is willing to sacrifice energy to make, but we don't know how or why life is even making it. So absolutely mysterious, absolutely deadly, smells horrifically. When it's made, it produces other kind of diphosphines, and it's been reported as smelling like garlicky, fishy death. Once someone referred to it as smelling like let me see if I remember, the rancid diapers of the spawn of Satan.
Oh, very nice.
Yeah, very, very vivid. And so...
See, you're a poet after all.
I didn't call it that. Someone else did.
Right.
And so it's just this horrific molecule, but it is produced by life. We don't know why. And when it is produced by life, it's done with enormous sacrifice. And the universe does not sacrifice. Life sacrifices. And so it's this strange, contradictory molecule that we should all be avoiding, and yet seems to be almost an ambiguous sign of life on rocky planets.
Okay, can we dig into that a little bit? So, what on rocky planets? What is there biological mechanisms that can produce it? I mean, is there? You said that why is unclear. Why life might produce it, but is there an understanding of what kind of mechanisms might be able to produce it? This very difficult to produce molecule.
We don't know yet. The enzymatic pathways of phosphine production by life are not yet known. This is not actually as surprising as it might sound. I think something like 80% of all the natural products that we know of, so we know biology makes them, we don't know how. It is much easier to know life produces something because you can put, bacteria in a petri dish and then watch, and then that gas is produced. You go, oh, life made it. Yeah. That actually happened with phosphine. But that's much easier to do, of course, than figuring out what is the exact metabolic pathway within that life form that created this molecule. So we don't know yet. Phosphine is really understudied. No one had really heard of it until nowish.
What you were presenting is the fact that life produces phosphine, not the process by which it produces phosphine. Is there an urgency now? Like if you were to try to understand the mechanisms, what did you call them? Enzymatic pathways that produce phosphine, how difficult is that of a problem to crack?
It's really difficult. If I'm not mistaken, even, the scent of truffles, obviously a billion-dollar industry, huge deal. Until quite recently, it wasn't known exactly how those scents, those molecules that create this incredible smell were produced. And this is a billion-dollar industry. Wow. As you can imagine, there is no such pressure. There's no phosphine lobby or anything that would push for this research. But I hope someone picks it up and does it. And it isn't crazy because we know that phosphine is really hard to make. We know it's really hard for it to happen accidentally. Even lightning and volcanoes that can produce small amounts of phosphine. It's extremely difficult for even these extreme processes to make it. So it's not really surprising that only life can do it because life is willing to make things at a cost.
So maybe on the topic of phosphine, what again, you've gotten yourself into trouble that I'm going to ask you all these like high level poetic questions. I apologize.
No, but I would love it.
Okay. When did you first fall in love with phosphine?
It wasn't love at first sight. It was somewhere between a long relationship and Stockholm syndrome.
Yeah.
When I first started my PhD, I knew I wanted to learn about molecular spectra and how to simulate it. I thought it was really outrageous that we as a species couldn't detect molecules remotely. We didn't have this perfect catalog ready of the molecular fingerprint of every molecule we may want to find in the universe. And something as basic as phosphine, the fact that we didn't really know how it interacted with light, and so we couldn't detect it properly, in the galaxy. I was so indignant. And so initially I just started working on phosphine because people hadn't before. And I thought we should know what phosphine looks like. And that was it. And then I read every paper that's ever been published about phosphine. It was quite easy because there aren't that many. And that's when I started learning about where we had already found it in the universe and what it meant. I started finding out quite how little we know about it and why. And it was only when I joined MIT and I started talking to biochemists that it became clear that phosphine wasn't just weird and special and understudied and disgusting. It was all these things for oxygen-loving life. And it was the anaerobic world that would welcome phosphine. And that's when the idea of looking for it on other planets became crystallized. Because oxygen is very powerful and very important on Earth, but that's not necessarily going to be the case on other exoplanets. Most planets are oxygen poor. Overwhelmingly, most planets are oxygen poor. And so finding this sign of life that would be welcomed by everything that would live without oxygen on Earth seemed so cool.
But ultimately, the project at first was born out of the idea that you want to find that molecular fingerprint of a molecule. So, and that this is just one example, and that's connected to then looking for that fingerprint elsewhere in a remote way. And obviously that then at that time were exoplanets already when you were doing your PhD, and you, by the way, I should say your PhD thesis was on
it was all on phosphine, 100% on phosphine, with a little bit of ammonia. I have a chapter that I did where I talked about phosphine and ammonia. So I
got it.
But no, phosphine was very much my thesis.
But at that time when you were writing it, there was already a sense that exoplanets are out there, and we might be able to be looking for biosignatures for on those exoplanets.
Pretty much. So I finished my PhD in 2015. Mm-hmm. We found the first exoplanets in the kind of mid to late 90s. So exoplanets were known. It was known that some had atmospheres. And from there, it's not a big jump to think, well, if some have atmospheres, some of those might be habitable, and some of those may be inhabited.
So how do you detect, you started to talk about it, but can we linger on it? How do you detect phosphine on a faraway thing, rocky planet? What is spectroscopy? What is this molecular fingerprint? What does it look like? You've kind of mentioned a wave, but what are we supposed to think about? What are the tools? What are the uncertainties? All those kinds of things.
So the path can go this way. You've got light, kind of pure light. You can crack that light open with a prism or a spectroscope or water and make a rainbow. That rainbow is all the colors and all the invisible colors, the ultraviolet, the infrared. And if that light was truly pure, you could consider that rainbow to just cover continuously all of these colors. But if that light goes through a gas, we may not see that gas. We certainly cannot see the molecules within that gas. But those molecules will absorb some of that light. Some, but not all. Each molecule absorbs only very specific colors of that rainbow. And so if you know, for example, that shade of green can only be absorbed by methane, then you can watch as a planet passes in front of a star. The planet's too far away, you can't see it. And it has an atmosphere. That atmosphere is far too small, you definitely can't see it. But the sunlight will go through that atmosphere. And if that atmosphere is methane, then on the other side, that shade of blue, I can't remember if I said blue or green, but that color will be missing because methane took it. And so with phosphine, it's the same thing. It has specific colors, 16.8 billion colors, that it absorbs it and nothing else does. And so if you can find them and notice them missing from the light of a star that went through a planet's atmosphere, then you'll know that atmosphere contains that molecule. How cool is that?
That's incredible. So you can have this fingerprint within the space of colors, and there's a lot of molecules. And I mean, I wonder, that's a question of like how much overlap there is. How close can you get to the actual fingerprint? Like, can phosphine unlock the iPhone with its light, so on? He says 16.8 billion. So presumably this rainbow is discretized into little segments somehow.
Exactly.
How many total are there? How a lot is 16.8 billion?
It's a lot. We don't have the instruments to break any light into this many tiny segments. And so with the instruments we do have, there's huge amounts of overlap. Methane, as an example, a lot of the ways it's detectable is because the carbon and the hydrogens, they vibrate with one another, they move, they interact. But every other hydrocarbon, acetylene, isoprene, has carbon and hydrogens also vibrating and rotating. And so it's actually very hard to tell them apart at low resolutions. And our instruments can't really cope with distinguishing between molecules particularly well. But in an ideal world, if we had infinite resolution, then yes, every molecule's spectral features will be unique.
Yeah, like almost too unique. Like it would be too trivial.
At the quantum level.
At the quantum level, yes.
At our level, there's huge overlap.
Yeah. But then you can start to then, try to disambiguate, like what the fact that certain colors are missing, what does that mean? And hopefully they're missing in a certain kind of pattern where you can say with some kind of probability that it's this gas, not this gas.
Exactly.
So you're solving that gaseous puzzle. I got it. Okay.
We can go back to Venus, actually, and show that. So with this, I mentioned there was two molecules that could be responsible for that signal, the resolution that we have. It was phosphine and SO2, sulfur dioxide. And at that resolution, it could really be one or the other. But in that same bandwidth, so in the kind of the same observations, there was another region where phosphine does not absorb. We know that. But SO2 does. So we just went and checked, and there was no signal. So we thought, oh, then it must be phosphine. And then we submitted the paper. The rest is history.
I got it. Well, yeah, that's beautifully told. Is there, so the telescopes we're talking about are sitting on Earth. What can it help solving this molecular fingerprint problem if we do a flyby? Does it help if we get closer and closer? Or are telescopes pretty damn good for this kind of puzzle solving?
Telescopes are pretty good, but the Earth's atmosphere is a pain. I mean, I'm very thankful for it. But it does interrupt a lot of measurements, and a lot of regions where phosphine would be active, they are not available. The Earth is not transparent in those wavelengths. So being above the atmosphere would make a huge difference. Then proximity matters a lot less, but just escaping the Earth's atmosphere would be wonderful. But then it's really hard to stay very stable. And if there is phosphine on Venus, there's very little of it in the clouds. And so the signal is very weak. And the telescopes we can use on Earth are much bigger and much more stable. So it's a bit of a trade-off.
So is it... Are you comfortable with this kind of remote observation? Is it at all helpful to strive for going over to Venus and like grabbing a scoop of the atmosphere? Or is remote observation really a powerful tool for this kind of job? Like the scoop is not necessary.
Well, a lot of people want to scoop. I get it.
Yeah,
I get it
that's
completely.
My natural inclination, yeah.
I don't want to scoop specifically because if it is life, I want to know everything I can remotely before I interfere. Yeah. So that's I've got ethical reasons against the scoop more than engineering reasons against the scoop. But I have some engineering reasons against the scoop. Scoop is not a technical term, but I feel like now it's too late.
Thank you for going along with this.
It's too late to take it back.
I appreciate it.
We don't understand the clouds well enough to plan the scoop very well.
Because it's not that saturated, like there's not that much of it present.
No, and the place is nasty. You know, it's not going to be easy to build something that can do the task reliably and can be trusted. The measurements can be trusted, and then pass that message on. So actually, I'm for an orbiter. I think we should have orbiters around every solar system body whose job is just to learn about these places. I'm disappointed we haven't already got an orbiter around every single one of them. It can be a small satellite. Just collecting data, figuring out, how do the clouds move? What's in them? How often is there lightning and volcanic activity? Where's the topography? Is it changing? Is there a biosphere actively doing things? We should be monitoring this from afar. And so I'm for over the atmosphere, hopefully around Venus. That would be my choice. Okay,
so now recently Venus is all exciting about phosphine and everything. Is there other stuff maybe before we were looking at Venus or now looking out into other solar systems? Is there other promising exoplanets or other planets within the solar system that might have phosphine or might have other strong biosignatures that we should be looking for, like phosphine?
There's a few, but outside the solar system, all are kind of promising candidates. We know so little about them. For most of them, we barely know their density. Most of them, we don't even know if they have an atmosphere, never mind what that atmosphere might contain. So we're still very much at the stage where we have detected promising planets, but they're promising in that they're about the right size, the right density. They could have an atmosphere, and they're about the right distance from their host star. But that's really all we know. Near future telescopes will tell us much more, but for now, we're just guessing.
So you said near future. So there's hope that there will be telescopes that can see that far enough to determine if there's an atmosphere and perhaps even the contents of that atmosphere?
Absolutely. JWST, launching later this year, will be able to get a very rough sense of the main atmospheric constituents of planets that could potentially be habitable. And that's this year.
What's the name of
JWST, the James Webb Space Telescope.
Okay. And that's going to be out in space, past the atmosphere.
Yes.
Is there something interesting to be said about the engineering aspect of the telescope?
It's an incredible beast, but it's a beast of many burdens. So it's going to do... it's going.
See, you are a poet. Yeah. I love it. This is very eloquent. You're speaking to the audience, which I appreciate. So it's a giant engineering project. And is it orbiting something? Do you know?
So it's going to be above the atmosphere. And it will be doing lots of different astrophysics. And so some of its time will be dedicated to exoplanets. But there's an entire astronomy field fighting for time before the cryogenic lifetime of the instrument. And so when I was looking for the possibility of finding phosphine on distant exoplanets, I used JWST as a way of checking with this instrument that we will launch later this year. Could we detect phosphine on an oxygen-poor planet? And there I put very much a hard stop where some of my simulations said, yes, you can totally do it, but it will take a little under the cryogenic lifetime of this machine. So then I had to go, well, that's not going to, no one's going to dedicate all of JWST to look for my molecule that no one cared about. So we're very much at that edge, but there'll be many other telescopes in the coming decades that will be able to tell us quite a lot about the atmospheres of potentially habitable planets.
So you mentioned simulation. This is super interesting to me. And this perhaps could be a super dumb question, but...
No such thing.
I'm going to prove you wrong on that one. You simulate molecules to understand how they look from a distance, is what I understand. Like, what does that simulation look like? So it's talking about the which colors of the rainbow will be missing. Is that the goal of the simulation?
That's the goal, but it's really just a very, very nasty Schrodinger's equation. So it's a quantum simulation.
Oh, so it's simulating at the quantum level.
Yes. So I'm a quantum astrochemist. Hi, I'm Clara. I'm a quantum astrochemist. That's how we should have started this conversation.
Can you describe the three components of that quantum astro and chemist and how they interplay together?
So I study the quantum behavior of molecules, hence the quantum and the chemist, specifically so I can detect them in space, hence the astro. So what I do is I figure out the probability of a molecule being in a particular state. There's no deterministic nature to the work I do. So it's every transition is just a likelihood. But if you get a population of that molecule, it will always happen. And so this is all at the quantum level. It's a Schrödinger equation on, I think, 27 dimensions. I don't remember it by heart. And what this means is I'm solving these giant quantum matrices. And that's why you need a lot of computer power, giant computers, to diagonalize these enormous matrices, each of whom describes a single vibrational behavior of a molecule. So I think phosphine has 17.5 million possible states it can exist in. And transitions can occur between pairs of these states. And there's a certain likelihood that they'll happen. This is the quantum world. Nothing is deterministic. There's just a likelihood that it will jump from one state to another. And these jumps, they're transitions. And there's 16.8 billion of them. When energy is absorbed, that corresponds to this transition. We see it in the spectrum. This is more quantum chemistry than you had asked for. I'm sorry.
No, I'm sorry. Brain's broken. So when the transitions happen between the different states, somehow the energy maps to the spectrum.
Exactly. Energy corresponds to a frequency, and a frequency corresponds to a wavelength, which corresponds to a color.
So there's some probability assigned to each color then?
Exactly. And that probability determines how intense that transition will be, how strong.
And so you run this kind of simulation for particular So that's 17.5 squared or something like that.
Exactly. 17.5 million energies, each one of whom involves diagonalizing a giant matrix with a supercomputer.
Actually, I wonder what the most efficient algorithm for diagonalization is. But there's some kind
There's
of...
many.
There's many, yeah.
Depends on kind of the shape of the matrix. So they're not random matrices. So some are more diagonal than others. And so some need more treatment than others. Most of the work ends up going in describing this system, this quantum system, in different ways until you have a matrix that is close to being diagonal. And then it's much easier to clean it up.
So how hard is this puzzle? So you're solving this puzzle for phosphine, right? Are we supposed to solve this puzzle for every single molecule? Oh boy.
Yes, I calculated if I did the work I did for phosphine, again, for all the molecules for which we don't have spectra, for which we don't have a fingerprint, it would take me 62,000 years, a little over.
62,000 years. Well, time flies when you're having fun. Okay, but you write that there are about 16,000 molecules we care about when looking for a new Earth or when we try to detect alien biosignatures. If we want to detect any molecules from here, we need to know their spectra, and we currently don't. Solving this particular problem, that's my job.
Where was that? That's absolutely correct. Yeah. I could have not said it better myself. Did you take that from my website?
Yeah, I think I stole it. And your website is excellent, so it's a worthy place to steal stuff from.
Thank you.
How do you solve this problem for the 16,000 molecules we care about, of which phosphine is one?
Yes.
And so, taking a step a little bit out of phosphine, is there...
But we were having so much fun.
We were having so much fun. No, we're not saying
no,
it's sticking around. I'm just saying we're joining more friends coming to the party. How do you choose other friends to come to the party that are interesting to study as we solve one puzzle at a time through the space of 16,000?
So we've already started. Out of those 16,000, we understand water quite well, methane quite well, ammonia quite well, carbon dioxide. I could keep going. And then we understand molecules like acetylene, hydrogen cyanide, more or less. And that takes us to about 4% of those 16,000. We understand about 4% of them, more or less. Phosphine is one of them. But the other 96%, we just really have barely any idea at all of where in the spectrum of light they would leave a mark. I can't spend the next 62,000 years doing this work, and I don't want to. Even if somehow I was able, that wouldn't feel good. So one of the things that I try to do now is move away from how I did phosphine. So I did phosphine really the best that I could, the best that could be done with the computer power that we have. Trying to get each one of those 16.8 billion transitions mapped, accurately calculated. And then I thought, what if I do a worse job? What if I just do a much worse job? Can I just make it much faster and then it's still worth it?
Yes.
Like, how bad can I get before it's worthless? And then could I do this for all the other molecules?
Yes.
So I created exactly this terrible system.
What's the answer to that question, that fundamental question I ask myself all the time in other domains?
How crappy can I be before I'm useless?
Before somebody notices.
Turns out pretty crappy, because no one has any idea of what these molecules look like. Anything is better than nothing. Mm-hmm. And so I thought, how long will it take me to create better than nothing spectra for all of these molecules? And so I created RASCAL, Rapid Approximate Spectral Calculations for all. And what I do is I use organic chemistry and quantum chemistry and kind of cheat at them both. I just try to figure out what is the fastest way I could run this. And I simulate rough spectra for all of those 16,000. So I've managed to get it to work. It's really shocking how well it works, considering how bad it is.
Is there insights you could give to the tricks involved in making it fast? Like, what are the maybe some insightful shortcuts taken that still result in some useful information about the spectra?
The insights came from organic chemistry from decades ago. When organic chemists wanted to know what a compound might be, they would look at a spectrum and see a feature, and they would go, I've seen that feature before. That's usually what happens when you have a carbon triple bonded to another carbon. And they were mostly right. Almost every molecule that has a carbon triple bonded to another one looks like that. Has other features different that distinguish them from one another, but they have that feature in common. We call these functional groups. And so most of that work ended up being abandoned because now we have mass spectrometry, we got nuclear magnetic resonance spectroscopy, so people don't really need to do that anymore. But these ancient textbooks still exist, and I've collected them all, as many as I could. And there are hundreds of these descriptions where people have said, oh, whenever you have a iodine atom connected to this one, there's always a feature here. And it's usually quite sharp and it's quite strong. And some people go, oh, yeah, that's a really broad feature every time that combination of atoms and bonds. So I've collected them all. And I've created this giant dictionary of all these kind of puzzle pieces, these Lego parts of molecules. Mm-hmm. And I've written a code that then puts them all together in some kind of like Frankenstein's monster of molecules. So you ask me for any molecule, and I go, well, it has these bonds and this atom dangling off this atom and this cluster here. And I tell you what it should look like. And it kind of works.
So this creates a whole portfolio of just kind of signatures that we could look for.
Very rough signatures.
But still useful enough to analyze the atmospheres, the telescope-generated images of other planets?
Close. Right now, it is so complete, so it has all of these molecules, that it can tell you, say you look at an alien atmosphere and there's a feature there. It can tell you, oh, that feature, that's familiar. It could be one of these 816 molecules.
And there's
Best of luck.
Yes.
So I think the next step, which is what I'm working on, is telling you something more useful than it could be one of those 816 molecules. That's still true. I wouldn't say it's useful. So it can tell you, but only 12% of them also have a feature in this region, so go look there. And if there's nothing there, it can't be those, and so on. It can also tell you things like, you will need this much accuracy to distinguish between those 816. So that's what I'm working on, but it's a lot of work.
So this is really interesting, the role of computing in this whole picture. You mentioned code. So like you as a quantum astrochemist, there is some role for programming in your life, in your past life, in your current life?
Oh yeah, almost entirely. I'm a computational quantum astrochemist, but that doesn't roll off the tongue very easily.
So this is fundamentally computational. Like if you want to be successful in the 21st century in doing quantum astrochemistry, you want to be computational?
Absolutely. All quantum chemistry is computational at this point.
Okay. What, does machine learning play a role at all? Is there some extra shortcuts that could be discovered through, like you see all that success with protein folding, right? A problem that thought to be extremely difficult to apply machine learning to because it's, mostly because there's not a lot of already solved puzzles to train on. I suppose the same exact thing is true with this particular problem, but is there hope for machine learning to help out?
Absolutely. Currently, you've laid out exactly the problem. The training set is awful. And because a lot of this data that I'm basing it on is literally many decades old. The people who worked on it and data that I get, often they're dead. And the files that I've used, some of them were hand-drawn by someone tired in the 70s.
Yes.
So I can, of course, have a program training on these, but I would just be perpetuating these mistakes without hope of actually verifying them. So my next step is to improve this training set by hand and then try to see if I can apply machine learning on the full code of the full 16,000 molecules and improve them all. But really, I need to be able to test the outcomes with experimental data, which means convincing someone in a lab to spend a lot of money putting very dangerous gases in chambers and measuring them at outrageous temperatures. So it's a work in progress.
And so collecting huge amounts of data about the actual gases You are up for doing that kind of thing too. So actually, like doing the full end to end thing, which is like having a gas, collecting data about it, and then doing the kind of analysis that creates the fingerprint, and then also analyzing using that library the data that comes from other planets. So you do the
full from birth to death.
Interesting.
Yes, I worked
That's
in an
fascinating.
industrial chemistry laboratory when I was much younger in Slovenia. And there I worked in the lab actually collecting spectra and predicting spectra.
What's it like to work with a bunch of gases that are like not so human friendly? Is it
Terrifying. It's horrific. It's so scary. And I love my job. I'm willing to clearly sacrifice a lot for
Yes.
it. You know, job, stability,
Yeah.
money,
Yes.
sanity. But I only worked there for a few months. It was really terrifying. There's just so many ways to die. You know, usually you only have a handful of ways to die every day, you know, but if you work in a lab, there's so many more, like orders of magnitude more. And I was very bad at it. I'm not a good hands-on scientist. I want a laptop connected to a remote supercomputer or a laptop connected to a telescope.
Yes.
I don't need to be there to believe it. And I am not good in the lab.
Yeah, when there's a bunch of things that can poison you, a bunch of things that could explode, and they're gaseous, and they're often, maybe they might not even have a smell, or they might not be visible. It's like
So many of them give you cancer. It's just so cruel. And some people love this work, but I've never enjoyed experimental work. It's so ungrateful. It's so lonely.
well, so much work is lonely if you find the joy in it, but you enjoy the results of it.
Yes. I'm very thankful for all the experimentalists in my life. But I'll do the theory, they do the experiment, and then we talk to one another and make sure it matches, you know?
Okay, beautiful. What are spectroscopic networks? Those look super cool. Are they related to what we were talking about? The pictures look pretty.
Oh, yes, slightly. So remember when I mentioned the 17.5 million energy levels?
Yes.
There are rules for each molecule on which energy levels it can jump from and to, and how likely it is to make that jump. And so if you plot all the routes it can take, you get this energy network, which is like a ball.
Mm-hmm.
of
So these are the
points.
constraints of the transitions that could be taken.
Exactly for each molecule.
Interesting. And they're not, so it's not a fully connected, it's like, it's sparse somehow. Like,
Yes, you get islands sometimes. You get
oh,
a
cool.
molecule can only jump from one set of states to another, and it's trapped now in this network. It can never go to another network that could have been available to other siblings.
Is there some insights to be drawn from these networks? Like something cool that you can understand about a particular molecule because of it?
Yes, some molecules have what we call forbidden transitions, which aren't really forbidden because it's quantum. There are no rules. No, I'm not. There are rules. It's just the rules are very often broken in the quantum world.
Yeah.
And so forbidden transitions doesn't actually mean they're forbidden.
Low probability.
Exactly. They just become deeply unlikely.
Yeah. Cool. And then, so you could do all the same. Like I'm coming from a computer science world, you know, I love graph theory. So you can do all the same, like graph theoretic kind of analysis of like clusters or something like that,
Exactly.
or all those kinds of things, and draw insights from it.
And
Cool.
they're unique for each molecule. So the networks that you mentioned, that's actually not too difficult a layer of quantum physics. By then, all the energies are mapped. So we've had high school children work on those networks. And the trick is to not tell them they're doing quantum physics until like 3 months in, when it's too late for them to back out. And then you're like, you're a quantum physicist now. And it's really nice.
Yeah. Okay, but the promise of this, even though it's 16,000, even just a subset of them, that's really exciting because then you can do, as the telescope data get better and better, especially for exoplanets, but also for Venus, you can then start like getting your full, like, you know how you get like blood work done, or like you get your genetic testing to see what your ancestors are. You can get the same kind of like high resolution information about interesting things going on a particular planet based on the atmosphere, right?
Exactly. How cool would that be if we could, scan an alien planet and go, oh, this is what the clouds are made of. This is what's in the surface. These are the molecules that are mixing. Here are probably oceans, because you can see these types of molecules above it. And here are the Hadley cells. Here are how the biosphere works. We could map this whole thing.
Wouldn't it be cool if the aliens like are aware of these techniques and like would spoof like the wrong gases just to like pretend that's how they can be? It's like an invisibility cloak. They can generate gases that would throw you off, or do the opposite. They pretend they will artificially generate phosphine, so they like the dumb apes on Earth again, like go out like flying in different places because it's just fun. It's like some teenager alien somewhere just pranking. Yeah. But
I was asked that exact question this Saturday by a 7-year-old boy in Canada.
How old? 7?
7. Yeah.
Yes.
But it was the first time I'd been asked that question. This is the second in a week.
We're kindred spirits, him and I.
We can. They can prank us to some extent, but this work of interpreting an alien atmosphere means you're reading the atmosphere as a message. And it's very hard to hide signs of life in an atmosphere because you can try to prank us, but you're still going to fart and breathe and somehow metabolize the environment around you and call that whatever you call that and release molecules. And so that's really hard to hide. You know, you can go very quiet. You can throw out some weird molecule to confuse us further, but we can still see all your other metabolites.
Yeah. It's hard to fake. Is there? So you kind of mentioned like water. What other gases are there that we know about that are like high likelihood as biosignatures in terms of life? I mean, what are your other favorites? So we know we got phosphine, but like what else is a damn good signal to be that you think about that we should be looking for if we look at another atmosphere? Is there gases that come to mind, or are there all sort of possible biosignatures that we should love equally?
There's many. So there's water. We know that's important for life as we know it. There's molecular oxygen on Earth. That's probably the most robust sign of life, particularly combined with small amounts of methane. And it's true that the majority of the oxygen in our atmosphere is a product of life. And so if I was an alien astronomer and I saw Earth's atmosphere, I would get a Nobel, I think, on,
What would you notice? I mean, this is really...
I would be very excited about this.
About the oxygen.
About finding 20%, 21% of oxygen in the atmosphere. That's very unusual.
So would that be the most exciting thing to you from an alien perspective about Earth in terms of like analyzing the atmosphere? Like what are the biosignatures of life on Earth, would you say, in terms of the contents of the atmosphere? Is oxygen, high amount of oxygen, pretty damn good sign?
I mean, it's not as good as the TV signals we've been sending out.
Sure.
Those are slightly more robust than oxygen. Oxygen on its own has false positives for life, so there's still ways of making it. But it's a pretty robust sign of life in the context of our atmosphere with the radiation that the sun produces, our position in relation to the sun, the other components of our atmosphere, the volcanic activity we have, all of that together makes the 20% of oxygen extremely robust sign of life. But outside that context, you could still produce oxygen without life. But phosphine, although better in the sense of it is much harder to make, it has lower false positives, still has some. So I'm actually against looking for specific molecules. Unless we're looking for like CFCs. If we find CFCs, that's definitely aliens. I feel confident. Chlorofluorocarbons. And so, if aliens had been watching us, they would have been going, oh no, CFCs. I mean, they're not going to last long. Let's, everyone's writing their thesis on the end of the Earth. And then we got together. We stopped using them. I like to think they're really proud of us. They literally saw our ozone hole shrinking. They've been watching it and they saw it happen.
I think, to be honest, they're more paying attention to the whole nuclear thing.
I don't think they care. It's not going to bother them. Oh, I mean, worried about us. Oh, yes.
Oh, no, worried about us. This is why the aliens have been showing up recently. It's like if you look at, it's probably there's a correlation with a lot of things. But what the ufologists, quote unquote, often talk about is that there seems to be a much higher level of UFO sightings since like in the nuclear age. So like if aliens were indeed worried about us, Like if you were aliens, you would start showing up when the living organisms have first discovered a way to destroy the entire colony.
Can the increase in sightings not have to do with the fact that people now have more cameras?
It's an interesting thing about science. Like with UFO sightings, it's like either 99.9% of them are false or 100% of them are false. The interesting thing to me is that in that 0.01%, there's a lot of things in science that are like these weird outliers. They're difficult to replicate. You have there's even physical phenomena, ball lightning. There's difficult things to artificially create in large amounts or observe in nature in large amounts in such a way that you can apply the scientific method. There could be just things that happen a few times, or once, and you're like, what the hell is that? And that's very difficult for science to know what to do with. I'm a huge proponent of just being open-minded, because when you're open-minded about aliens, for example, it allows you to think outside of the box in other domains as well. And somehow that will result, if you're open-minded about aliens and you don't laugh it off immediately, what happens is somehow that's going to lead to a solution to P equals NP or P not equals NP, in ways that you can't predict. The open-mindedness has tertiary effects that will result in progress, I believe, which is why I'm a huge fan of aliens, because it's because too many scientists roll their eyes at the idea of aliens, alien life. And to me, it's one of the most exciting possibilities and the biggest, most exciting questions before all of human civilization. So to roll your eyes is not the right answer. To roll your eyes presumes that you know anything about this world, as opposed to just knowing 0.0001% of this world. And so being humble in the face of that, being open to the possibility of aliens visiting Earth is a good idea. Not everything, though. I'm not so open-minded to the flat Earth hypothesis as there's a growing number of people believing in. But even then...
Or the inner Earth. I've got shouted at a public talk about it.
So the Earth is hollow?
Yeah, my understanding is that there's this conspiracy theory that, as far as I can tell, has no grounding in reality, is that there's a slightly smaller Earth inside this one, which is just too cute as a concept.
Oh, that's awesome.
And you can access it, I think, from Antarctica. And that's where we keep, and I quote, the mammoths and the Nazis.
Yeah, I mean, that one is ridiculous. But I do like...
Hey, I thought you were keeping an open mind.
I am. This is
I genuinely think that's more likely than aliens visiting the Earth. And I say this as someone who has dedicated her life to finding alien life. And so that's how improbable I think the visitations are. Because interstellar distances are so huge that it's just not really worth it.
See, I have a different view on this whole thing. I think the aliens that look like little green men are extremely low probability event.
Mammoths and Nazis under?
That's similar.
That level. Okay.
But other kind of ideas, the sad thing to me, and I think in my view, if there's other alien civilizations out there and they visited Earth, neither them or perhaps just us would be even able to detect them. We wouldn't be open-minded enough to see it. Because our understanding of what is life, and I just talked to Sarah Walker, who's
you know Sarah.
Yeah, we talked for 3 hours about the question of what is life.
Sarah's a good person to talk to about what is life. So.
But the whole point is we have a very narrow-minded view of what is life, and when it shows up, and it might be already here, trees and dolphins and so on.
Choices.
And or mountains, or I don't know, or the molecules in the atmosphere, or people make fun of me, but I do think that ideas are kind of aliens themselves, or consciousness could be the aliens, or it could be the method by which they communicate. We don't know shit about the way our human mind works, and the fact that this thing is
be a quantum process.
Please don't. I understand this. It's not woo woo. I'm not. It could, but it very well could be. There could be something at the physics level, right? It could be at the chemical or the biological level. Things that are happening that we're just too close minded, because our conception of life is at the level of like us, like at the jungle level of mammals, and on the time scale that's the human time scale. We may not be able to perceive what alien life is actually like, the scale at which their intelligence realizes itself. We may not be able to perceive. And the other thing that's really important about alien visitations, whether it happened or not, is especially after COVID in 2020, I'm losing a little bit of faith of our government being able to handle that well. Not our government, but us as a society, as a collective, being able to deal with new things in an effective way that's inspiring, that's efficient, that like whether it's if it's a dangerous thing, to deal with it, to alleviate the danger, whether it's the possibility of new discoveries and something inspiring, to ride that wave and make it inspiring, all those kinds of things. I honestly think if aliens showed up, they would look around, everybody would ignore them, and the government might like hide it, try to like to keep it from the Chinese and the Russians if it's the United States, to call it a military secret in a very close-minded way. And then the bureaucracy would drown it away to where through paperwork, the poor aliens would just like waste away in a cell somewhere. Like there's a certain...
That would not happen. That would never happen. Part of the reason that I feel so confident that aliens have not visited is because they would have had to visit just to have a look remotely, from Neptune or something. Which makes no sense because interstellar travel is so difficult that it would be quite a ridiculous proposition. But that's the bit that I think is technically possible. If they did come here and they were visible by anyone, detectable by anyone, the thought that any government, no matter, or any military could just contain them, these beings are capable of traveling interstellar distances when we can barely go to the moon, barely go to the moon.
So these things would be way more intelligent.
And the fact that we think our puny military, even if all the military in the world got together, and the fact that they could somehow contain this, that's
like
the
ants
bit
trying
that's
to contain a human that visited them.
Exactly.
But
and scientists. You would have to bring scientists on board. You've met a lot of scientists.
Yeah.
How good are they at keeping secrets? Because in my experience, they're absolutely appalling at keeping secrets.
Yeah, that's terrible.
Even the Phosphine on Venus thing, which was a pretty well-kept secret.
Oh, this is true. You had a bunch of people that were...
I told my dad.
Yeah.
My dad knew. And hopefully didn't tell anyone. But if it had been an alien visiting, he probably would have told the mate, And so these secrets could not be kept by any scientist that I know, and certainly not collaborative scientists, which would be needed. You would need all sorts of scientific teams. So between the pathetic power of any world's military compared to any civilization capable of traveling, and our absolute inability to keep secrets, absolutely not. I will bet everything that we have not been visited because we are too pathetic to hold that.
Well, let me
hold that
back.
truth.
If we're making a $10 bet, the possibility here that the main alien, say there exists one other intelligent alien civilization in the galaxy. To me, if they visit Earth, what's going to visit Earth is like the crappy. Like the really crappy
short straw,
like this like really dumb thing that's I don't know, like the early Game Boys or something. Like,
I think there's a cartoon about this. There's an alien that gets sent to Earth, Commander Spiff or something, and it's kind of a punishment or something. But that's not possible. That's the thing, because interstellar distances are so hard to cross.
You have to do it on purpose.
You have to do it on purpose. It has to be a big, big deal. And we know this because, yes, you're right. We don't know enough about galactic biology. We don't know what the universal rules of biology or biochemistry are because we only have the Earth. But we do know that the laws of physics are universal. We can predict behavior in the universe and then see it happen based on these laws of physics. We know that the laws of chemistry are universal. We know the periodic table is all they have to choose from. So yes, they may be some sort of unimaginable intelligence, but they still have to use the same periodic table that we have access to. They still have a finite number of molecules they can do things with. So they still have to use the resources around them, the stars around them, the universe around them. And we know how much energy is in these places. And so, yes, they may be very capable beyond our wildest dreams, but they're still in the same universe. And we know a lot of those rules. We're not completely blind.
But there's a colleague of yours at Harvard, Kamran Vafa. He's a theoretical physicist. I don't know if you know him.
I've only joined Harvard about 6 months ago.
Okay. There's time to meet all the theoretical physicists. So he's a string theorist, but his idea is that aliens that are sophisticated enough to travel interstellar, like that, those kinds of distances, will figure out actually ways to hack the fabric of the universe enough to have fun in other ways. Like, this universe is too boring. Like, you would figure out ways to create other universes, or like you go outside the physics as we know it. So the reason we don't see aliens visiting us all over the place is they're having fun elsewhere. This is like way too boring. We humans think this is fun, but it's actually mostly empty space that no fun is happening. Like, there's no fun in visiting Earth for a super advanced civilization. So he thinks, like, if alien civilizations are out there, they found outside of our current standard models of physics ways of having fun that don't involve us. But
and that's probably true. But even the notion of visiting, that's so literally pedestrian. Of course, we want to go there because going there is the only thing we know. We see a thing we want to go there and get it.
Yeah.
But that is probably something they've no longer got need for. I specifically don't particularly want to go to space. Sounds awful. None of the things I like are going to be there. And my whole career is finding life and understanding the universe. So I care a lot. Mm-hmm. But I care about knowing about it. And I feel no need to go there to learn about it. Mm-hmm. And I think as we develop better tools, hopefully people will feel less and less a need to go everywhere that we know about. And I would expect any alien civilization worth their salt have developed observation tools and tools that allow them to understand the universe around them and beyond, without having to go there. This going is so wasteful.
Yeah, so more focus on the knowledge and the learning versus the colonization, like the conquering and all those kinds of things.
That's beneath them.
That's beneath them. Do you think there's in your hopeful search for life through phosphine and other gases, do you think there's other alien civilizations out there? First, do you think there's other life out there? First, do you think there's life in the solar system? Second, do you think there's life in the galaxy? And third, do you think there's intelligent life in the solar system or the galaxy outside of Earth?
So intelligent life, I have no idea. It seems deeply unlikely. Possible, but I'm not even sure if it's plausible.
So that's the special thing to you about Earth, is somehow intelligent life came to be.
Yes, and it's only, very briefly, probably extremely briefly.
You mean like it's always going to be like we're going to destroy ourselves?
Exactly.
Oh, boy.
And life will continue on Earth happily, probably more happily.
The trees and the dolphins will be here, I'm telling you.
And the cockroaches and the incredible fungi, they'll be fine. So life on Earth will be fine, was fine before us and will be fine after us. So I'm not that worried about intelligent life, but I think it is unlikely. Even on Earth is unlikely. Out of, 5 billion species across the history of the Earth?
Yes.
There's been one, an intelligent one, and for a blink of an eye, possibly not much longer than that. So I wouldn't bet on that at all. Though I would love it, of course. I wanted to find aliens since I was a little girl. And so, of course, I initially wanted to find ones that I could be friends with.
Yeah.
And I've had to let go of that dream because it's so deeply implausible.
But see, and sorry to interrupt, but the nice thing about intelligent alien civilizations, they may have more biosignatures than non-intelligent ones. So they might be easier to detect. That would be the hope.
On Earth, that's not the case, but it could be the case elsewhere.
Oh, it's not the case on Earth.
Most of the biosignatures we have on Earth are created by quite simple life. If you don't count pollution. Pollution is all us, baby.
So you don't see polluting gases as a possible, like...
I look for polluting gases. I would love to find polluting gases. Well, I'd be worried for them, of course, the same way I think about my alien colleagues all the time, looking at us, and I'm sure they worry about our pollutions. But it would be a really good, robust, unambiguous sign of life if we found complex pollutants. So I look for those too. Yeah. I just don't have any hope of finding them. I think intelligent life in the galaxy at the same time that we're looking is deeply implausible. But life, I think, is inevitable. And if it is inevitable, it is common. So I think there'll be life everywhere in the galaxy. Now, how common that life is, I think will depend a lot on whether there's life in the solar system beyond Earth. So I'll adjust my expectations very much based on there being life in the solar system. If there's life in the Venusian clouds, if there's life if there are biosignatures coming out of the plumes of Enceladus, if there's life on Titan.
Oh, yeah, that's right. Plumes of Enceladus. That's the Saturn one?
It's the moon that has the geysers that come out, and so you can't see under the subterranean oceans, but...
so it would be in the atmosphere. I was going to ask you about that one. Have you looked at that? Is that a hope for you to use the tools you're using with Rascal and other ways for detecting the 16,000 molecules that might be biosignatures to look at Enceladus?
Yes, that's absolutely the plan.
What's the limiting factor currently? Is it the quality of the telescopes? What's the quality of the data?
Yeah, the quality of the data, the observational data, and also the quality of Rascal and other associated things. So we're missing a lot of fundamental data to interpret the data that we get, and we don't have good enough data. But hopefully we will, in the coming decades, we'll get some information on Titan. We have Dragonfly going over. We'll get the plumes of Enceladus. We will look at the clouds of Venus, and there's other places. And so if we find any life or any sign of life ever, like on Mars, then I'll adjust my calculations and I'll say life is not just inevitable and common, but extremely common. Because all of these places we've mentioned, the subterranean oceans on Enceladus, the methane oceans of Titan, the clouds of Venus, the acidic clouds of Venus, these are places that are very different from the places where we find life on Earth, even the most extreme places. And so if life can originate in all of these completely different habitats, then life is even more resourceful than we thought.
Yeah, that's
which means it's everywhere.
That's really exciting if it's everywhere. If there's life on just one of the moons, if it's on Mars.
Anywhere in the solar system, and I will bet everything I own that every solar system, every planetary system has potential for habitability, because even if they don't have a habitable planet, they'll have moons around other giant planets, and there'll be so much life. So for me, that's the only thing to figure out now, whether life is inevitable and quite common throughout the galaxy or everywhere. Mm-hmm. But it's somewhere between those two. Intelligent life, I make no bets. And if I had to bet, I would be against.
See, to me, like 2 discoveries in the 21st century would change everything. One is, and maybe I'm biased, but one is a discovery of life in the solar system. I feel like that would change our whole conception of how unique we are in the universe. I think I'm much more eager than you are to jump from basic life to intelligent life. I feel like if there's life everywhere, like the odds are we cannot, like oh, I see. You're saying there could have been many intelligent civilizations out there, but they just keep dying out. It's like little...
Yeah, I was detecting them, ships in the night.
Ships in the night. Oh, that's ultra sad. Just like...
Is it sad?
A graveyard.
The Earth is not better for having us. Is it? It doesn't owe us anything. Would you be sad to find alien giraffes? Would you be disappointed if you found alien giraffes? because I would not.
No, well, giraffes, first of all, they look goofy with their necks and everything, but...
No, we do not shit on giraffes.
Okay.
Giraffes are wondrous animals, are deeply understudied. We still know so little about them because no one does PhDs in giraffes. I am disappointed I made a PhD in phosphine when people aren't doing PhDs in giraffes. We do not know enough about giraffes.
I think it was like Ricky Gervais that did a whole like long thing about...
Trust Ricky Gervais to talk about giraffes? That is not his expertise.
Yeah, but it's the stupid necks. It doesn't make any sense. I mean, that's
Giraffes
fine.
are very resourceful animals who do incredible things and can kick a lion.
Why don't you climb the tree? Why don't you climb the tree? You don't need to grow through the lengthy evolutionary process.
You're shitting on giraffes.
Okay.
Giraffes are wondrous animals.
I would very appreciate it.
Back.
I take it back. I apologize. I trust your expertise on this. The thing that makes humans really fascinating, and I think the Earth, but I'm a human, is we create.
Disclaimer.
Yeah, we create things that are. Yes, there's all the ugliness in the world. There's all the on the biological, on the chemical level. There's the pollution, but we create beauty. If you even from a physics perspective look at symmetry as somehow capturing beauty, the breaking of symmetries, stuff grounded in all the different definitions of symmetry, we're good at like creating things.
So are spiders.
But not giraffes. Okay. But yes, this is
spiders.
Yes,
there are spiders that create little bubbles of air so they can breathe underwater. They can literally scuba dive. There are spiders that can create parachutes so they can glide.
Yeah.
And talk about symmetry. Look what spiders can do. And I just thought of spiders, but if I was an alien species coming to Earth, there'll be plenty to wonder, and we would just be one
of the things.
Yeah, clunky.
Yeah.
Naked monkey.
Yeah, the ants might be even more fascinating.
The ants. Ants can figure out exactly through some emergent consciousness what the maximum distance between their trash, their babies, and their food is, just from without any of them knowing how to do this. And collectively, they've learned how to do this. If I was an alien species, I'll be looking at that.
Well, so that was the other thing I was going to mention. The second thing is I tend to believe we can engineer consciousness, but at the basic level, understand the source of consciousness. Because if consciousness is unique to humans, and if we can engineer it, that gives me hope that it could be present elsewhere in the universe. That's the other thing that makes, it's
Agreed.
An open question, that makes humans perhaps special, is not maybe the presence of consciousness, but somehow a presence of like elevated consciousness. It does, again, maybe human-centric, but it feels like we're more conscious than giraffes, for example, and spiders.
Yes, I won't deny that. There is something special about humans. They're my favorite species.
They are.
Okay. Some of my best friends are humans. I think highly of humans. It's great. I just don't have great hope for our longevity. And specifically, I don't have great hope given that we're the only species out of 5 billion that did this cool consciousness trick. I don't want to bet on finding a kinship elsewhere.
That's quite interesting to think about. I don't think I've even considered that possibility that there would be life in the solar system. So that indicates that very possibly life is like literally everywhere.
Yeah, everywhere it can happen, it does.
Yeah, and like especially what we're discovering with the exoplanets now, how numerous they are, or Earth-like, habitable quote unquote planets. There's like they're everywhere.
The most common type of planet is rocky, it seems.
And so, but I didn't consider the possibility that life is like literally everywhere, and yet intelligent life is nowhere long enough to communicate with each other, to form little clusters of civilizations that expand beyond the solar system and so on. Man, maybe becoming a multiplanetary species is a less likely pursuit than we imagine.
I agree.
But one of the things that makes humans beautiful is we hope.
But I hope for humanity. And one of the things I hope for is that we become less obsessed with conquering and we become less obsessed with spreading ourselves. I hope that we transcend that we're happy with the universe without having to go and take it. So you can hope for the species without hoping for a multiplanetary existence. That is only, I think, the drive of our most primitive instincts to go and take, to go and plant a flag somewhere. We love planting a flag somewhere. And maybe we could overcome that minor drive.
And once we do, the AI systems we build will destroy us because we're too peaceful, and they will go and conquer and plant the flags.
Best of luck to them. The cockroaches will be happy to keep to the business as they always have.
I tend to believe that robots can have the same elegance and consciousness and all the qualities of kindness and love and hope and fear that humans have.
In principle, they could, yes. I don't really trust the people who make them.
This is about the giraffe comment, isn't it? Okay.
I haven't forgiven you for shitting on giraffes. What have they done to you?
You, just as a small tangent, your master's thesis is also fascinating. Maybe we could talk about it for just a little bit. It's titled Influence of a Star's Evolution on Its Planetary System. So this interplay between a star and a planet, is there something interesting you could say about what you've learned about this journey that a star takes and the planets around it?
Well, when I was younger and I was told what would happen ultimately to the Earth as the sun expands towards a red giant and, Mercury would just fall in and then, Venus fall in and the sun doesn't care. And it just seemed I felt so small. I felt like the Earth and everything on it. It's just, the universe doesn't care. Even our sun doesn't care. And I think I felt like our sun should feel some sort of responsibility for its planets, you know?
Yeah.
And it just felt like such a violent and neglectful parent.
Yeah, it's like a parent eating its own children.
It's horrible. It's just a horrible notion. But it made me think, what if there's some sort of generation? And so at the time when I was doing my master's, there was a notion of the white dwarf cemetery, which is this idea that when stars become white dwarfs, that death is so horrible that planets, potentially habitable planets that could have been habitable before, they're now gone. There's no chance for life. But then I thought, what if life returns? Now it's a white dwarf. It's calmed down. It's not going to go anywhere. White dwarfs are very stable across universal timescales. And so could you have planets around a white dwarf that could themselves get life again? Mm-hmm. Life doesn't care. And so my work was basically killing dozens of planets thousands of times. I just ran thousands and thousands of N-body simulations.
Well, you simulated this?
Yeah, so I simulated the star growing and just eating all these planets up and just absolute chaos. The orbits of the planets would change as the star loses mass, so you would have Jupiter planets just crashing into the other planets, throwing them into the sun early. It was terrifying to watch these simulations. It was absolute carnage. But if you run thousands of these simulations, some systems find new balanced ways of staying alive. Some systems post-star death find stable orbits again for billions of years, more than enough for life to originate again. And so that was my idea during that time. That thesis was trying to explore this notion of life coming back and this idea of the universe doesn't care if you're here or not, and it will go about its business. Andromeda will crash into us and it doesn't care. No one cares if you're alive in the universe. And so letting go of that preciousness of life, I found very useful at that stage of my career. And instead, I just thought, what if life is inevitable? It doesn't matter that it came by 4 billion years ago. It can start again 4 billion years later. And maybe that is nice. Maybe that's where hope lies, the phoenix rising everywhere. Planets being destroyed and created, and we're here now. And others will be more or less here-ish. billions of years later.
So accepting the cycle of death and life, and yeah,
And not taking it personally.
not taking it personally.
The sun doesn't owe us anything.
Yeah.
It's not a bad parent. It's not a parent at all.
Yeah, I was looking at the work of Freeman Dyson and seeing how this universe eventually will just be a bunch of supermassive black holes before they also evaporate.
A bunch of tiny black holes too.
Yeah.
Absolute quiet. Everyone, all the black holes, a little too far away from one another to even interact until it's just silence forever. But until then, many, many cycles of death and destruction and rebirth.
And rebirth. You kept bringing up sort of coding stuff up. I wanted to ask two things. First of all, like what programming language do you like? And also what, because you're, as a computational quantum astrochemist, no,
that's correct.
Yeah, that's right. You're kind of, you could say you're actually understanding some exceptionally complicated things. With one of the things you're using is the tools of computation, of programming. Is there a device you can give to people? Because I know quite a few that have not practiced that tool and have fallen in love with a particular science, whatever it's biology and chemistry and physics and so on. And if they were interested in learning to program and learning to use computation as a tool in their particular science, is there advice you can give on programming, and also just maybe a comment on your own journey and the use of programming in your own life?
Well, I'm a terrible programmer. A lot of scientists, their programming is bad because we never learned formal programming. We learned science, physics, chemistry. And then we were told, oh, you have to get these equations modeled and run through a simulation. And you're like, oh, okay, so I'm going to learn how to code to do this. And you learn just as much as you need to run these simulations and no more. So they're rarely optimized. They're really clunky. 6 months later, you can't read your own code. Yeah. My variable names are extremely embarrassing. I still have error messages for different compilation errors that say things like, at least your dad loves you, Clara. It doesn't help me at all.
There's like humor.
Yeah.
Yes.
Just like you suck at coding, but there's other things in your life. So I'm a bad programmer. And so, if that will give hope to anyone else who's a bad programmer, I can still do pretty impressive science.
Yes.
But I think I started learning MATLAB and Java when I was in college. Mm-hmm. It did me no good at all. It has not been particularly useful. I learned some Fortran. That was very useful, even though it's really not a fun language because so much of legacy code is in Fortran. And so if you want to use other people's code who have now retired, Fortran will be nice. And then I used IDL to visualize. So that simulation and body simulation, that was all Fortran and IDL. But thankfully, since I've left college, I've just learned Python like a normal person, and that has been much nicer. So most of my code now is in Python.
I should also make a few quick comments. Well, so one is you say you're sort of bad at programming. I've worked with a lot of excellent scientists that are quote unquote bad at programming. They're not. It gets the job done. In fact, there's a downside to sort of especially getting a software engineering education. If I were to give advice, especially if you're doing a computer science degree and you're doing software engineering, is not to get lost in the like optimization of the correct. There's an obsession, you can see it in like Stack Overflow, of the correct way to do things. And I think you can too easily get lost in constantly trying to optimize and do things the correct way when you actually never get done. The same thing happens. You have like communities of people obsessed with productivity, and they keep researching productivity hacks, and then they spend like 90% plus of their time figuring out how to do things productively, and then never actually do anything. So there's a certain sense, if you focus on the task that needs to be done, that's what programming is for. So not over optimizing, not thinking about variable names in the following sense. Sometimes you think, okay, I'm going to write code that's going to last for decades. In reality, your code if it's well written or poorly written, will be very likely obsolete very quickly. The point is to get the job done really well. So there's a trade-off there that you have to make sure to strike. I should also comment as a public service announcement or a request, if there's any world-class Fortran or Cobalt programmers out there, I'm looking for them. I want to talk to you. Because I think
that will not be me. I'm a terrible Fortran programmer.
But it's fascinating because so much of the world in the past and still runs on these programming languages, and there's like no experts on it. So
they're all retiring.
Yeah.
I disagree slightly in that I think because I can get the job done, I'm a programmer. Yeah. But because no one else can look at my code and know how I got my job done, I'm a bad programmer. That's how I'm defining it.
Yes. Including yourself.
Including myself 6 months later. Yeah. I'm working with a new student right now, and she sent me some messages on Slack being like, what is this file that you've got with some functions I run? And I was like, this was from 2018. It wasn't that long ago. And I can no longer remember what that code does. I'm going to spend now 2 days reading through my own code and trying to improve it. And I do think that's frustrating. And so I think my advice to any young people who want to get into astronomy or astrobiology or quantum chemistry is that I certainly find it much easier to teach the science concepts to a programmer than the programming to a scientist. And so I would much, much faster hire someone who knows programming but barely knows where space is than teach programming to an astronomer.
Oh, that's fascinating. Yeah, okay. This is true. I mean, yeah, there's some basics. I'm focusing too much on the silver lining because the people that write like MATLAB code, single letter variable names, those kinds of things.
And it's accessibility, right? I want my code to be open source, and it is. It's on GitHub. Anyone can download it. But is it really open source if it's written so cryptically, so poorly, that no one can really use it to its full functionality? Have I really published my work? And that weighs on me. I feel guilty for my own inadequacies as a programmer. But you can only do so much. So I've already learned quantum chemistry and astrophysics. So,
I mean, there's all kinds of ways to contribute to the world. One of them is publication, but publishing code is a fascinating way to contribute to the world, even if it's very small, very basic element. Great code. I guess I was also kind of criticizing the software engineering process versus which is a good thing to do, is code that's readable, almost like without documentation. Exactly. It's readable. It's understandable. The variable names, the structure, all those kinds of things. And
that's the dream.
That's the dream. This is a dumb question. What do you... all right.
No, tell me your dumb question. I want to hear it.
Okay. This is the question about beauty. It's way too general. It's very impossible to. It's like asking, "What's your favorite band? What's your favorite music band?"
Oh, I thought you meant wavelength band. I was like, I definitely have favorite wavelength bands. Absolutely.
Well, it's hard to narrow down, huh? Okay. What to you is the most beautiful idea in science?
It's not a dumb question. Do you want to try that question again, proudly?
Okay. I have a really good question to ask you.
Okay, don't oversell it. Okay. I've got an okay question to ask you,
I have what to you is the most beautiful idea in science? Something you just find inspiring, or just maybe the reason you got into science, or the reason you think science is cool?
My favorite thing about science is kind of the connection between the scales. So when I was little and I wanted to know about space, I really felt that it would make me feel powerful to be able to predict the heavens, something so much larger than myself that felt really powerful. It was almost a selfish desire. And that's what I wanted. There was some control to being able to know exactly what the sky would do. And then as I got older and I got more into astronomy, and I didn't just want to know how the stars moved, I wanted to know how the planets around them moved. And then as I got deeper into that field, I really didn't care that much about the planets. I wanted to know about the atmospheres around the planets, and then the molecules within those atmospheres and what that might mean. So I ended up shrinking my scale until it was literally the quantum scale. And now all my work, the majority of my work, is on this insane quantum scale. And yet I'm using these literal tiny, tiny tools to try and answer the greatest questions that we've ever been able to ask. And this crossing of scales from the quantum to the astronomical, that's so cool, isn't it?
Yeah. It spans the entirety, the tiny and the huge. That's the cool thing about, I guess, being a quantum astrochemist, is you're using the tools of the tiny to look at the heavenly bodies, the giant stuff.
And the potential life out there, that this is the thing that connects us, that you can't escape the rules of the quantum world and how universal they themselves are, despite being probabilistic. And that makes me feel really pleased to be in science, but in a really humbling way. It's no longer this thirst for power. I feel less special the more work I do, less exceptional the more work I do. I feel like humans and the earth and our place in the universe is less and less exceptional. And yet I feel so much less lonely. And so it's been a really good trade-off that I've lost power, but I've gained company.
Wow, that's a beautiful answer. I don't think there's a better way to actually end it. You're right. I asked a mediocre question and you came through, you made the question good by a brilliant answer. You're the Michael Jordan and I'm who's the Dennis I'll be the Dennis Rodman. I
don't know enough about basketball. I mean, literally, you've reached the peak of my basketball knowledge because I know that those people are basketball.
But that's it.
Pros, I believe, but only because I watched Space Jam, I think.
Are there books or movies in your life long ago or recently? Do you have any time for books or movies? Had an impact on you? What ideas did you take away?
I absolutely have time for books and movies. I try as best I can to not work very hard. I mostly fail, I should point out. But I think I'm a better scientist when I don't work evenings and weekends. If I get 4 good hours in a day, I often don't. I often get 8 crappy hours. Emails, meetings, bad code, data processing. But if I can get 4 high-quality scientific hours, I just stop working for the day because I know it's diminishing returns after that. So I have a lot of time. I try to make as much time as I can.
Can you kind of dig into what it takes to be, 1, productive, 2, to be happy as a researcher? Because I think it's too easy in that world to because you have so many hats you have to wear, so many jobs. You have to be a mentor, a teacher, head of a research group, do research yourself. You have to do service, all the kinds of stuff you're doing now with education and
interviews.
Yeah. So as a public science, like being a public communicator, that's a job.
Yeah.
The whole thing.
Pays very poorly.
I'll pay you in Bitcoin. Okay.
I'll take Bitcoin.
So is there some advice you can give to the process of being productive and happy as a researcher?
I think sadly it's very hard to feel happy as a scientist if you're not productive. It's a bit of a trap. But I certainly find it very difficult to feel happy when I'm not being productive. It's become slightly better if I know my students are being productive, I can be happy. But I think a lot of senior scientists, once they get into that mindset, they start thinking that their student science is theirs. And I think this happens a lot of senior scientists. They have so many hats. As you mentioned, they have to do so much service and so much admin that they have very little time for their own science. And so they end up feeling ownership over the junior people in their labs and their groups. And that's really heartbreaking. I see it all the time. And that, I think I've escaped that trap. I feel so happy, even when I'm not productive, when my students are productive. I think that sensation I was describing earlier of they only need to be half as productive as me for me to feel like I've done my job for humanity. So that has been the dynamic I've had to worry about. But to be productive is not clear to me what you have to do. You have to not be miserable otherwise. I find it extremely hard when I'm having conflicts with collaborators, for example. I find it very hard to enjoy the work we do, even if the work is this, fantastical phosphine or things that I know I love. Still very difficult. So I think choosing your collaborators based on how well you get along with them is a really sound scientific choice. Having a miserable collaborator ruins your whole life. It's horrible. It makes you not want to do the science. It probably makes you do clumsy science because you don't focus on it. You don't go over it several times. You just want it to be over. And so I think in general, just not being a douchebag can get so much good science done. Just find the good people in your community and collaborate with them. Even if they're not as good scientists as others, you'll get better science out.
Yeah, don't be a douchebag yourself and surround yourself by other cool people.
Exactly. And then you'll get better science than if you had tried to work with 3 geniuses who are just hell to be around.
Yeah, I mean, there's parallel things like that. I'm very fortunate now. I was very fortunate at MIT to have friends and colleagues there that were incredible to work with. But I'm currently I'm doing a lot of fun stuff on the side, like this little podcast thing. And I mentioned to you, I think, robotics related stuff. I was at just the Boston Dynamics yesterday, checking out their robots. And I'm currently, I guess, hiring people to help me with a very fun little project around those robots.
You want to put an ad in?
No, I have more applications I can possibly deal with. There's thousands. So it's not an ad. It's the opposite. It's like
we need to put an ad out for someone to help you go through the applications.
Well, that too is already there. That over 10,000 people applied for that.
An infinite Matryoshka doll of application management.
But the point is, it's not exactly. The point is, like, what I'm very distinctly aware of is life is short, and productivity is not the right goal to optimize for, at least for me. The right goal to optimize for is how happy you are to wake up in the day and to work with the people that you do, because the productivity will take care of itself.
Agreed. And
so, like, it's so important to select the people well. And I think one of the challenges with academia, as opposed to sort of the thing I'm currently doing, is like saying goodbye is sometimes a little bit tougher, because
really tough.
Your colleagues are there. I mean, goodbye hurts. And then if you have to spend the rest, for many years to come, still surrounded by them in the community, it's tougher. It kind of puts extra pressure to stay in that relationship, in that collaboration. And in some sense, that makes it much more difficult, but it's still worth it. It's still worth it to break ties if you're not happy, if there's not that magic, that dance. I talked to there's a guy named Daniel Kahneman.
Oh, I know. Danny Kahneman.
Danny, yeah. Boy, did that guy make me realize, like, what a great collaborator is.
Well, he had Tversky, right?
Yeah, but so they had a really deep collaboration there, but like I collaborated with him on a conversation, like just like talking about, I don't know what we were talking about. I think cars, autonomous vehicles, but the brainstorming session, I'm like a nobody. And the fact that he would, with that childlike curiosity and that dance of thoughts and ideas and the push and pull and the lack of ego, but then enough ego to have a little bit of a stubbornness over an idea and a little bit of humor and all those things. It's like, holy shit, that person. Also, the ability to truly listen to another human. It's like, okay, that's what it takes to be a good collaborator. It like made me realize that I've been very fortunate to have cool people in my life, but there's like levels even to the cool.
Yeah, I don't think you can compete with Danny Kahneman on cool. He's just incredible.
But it was like, okay, like, I guess what I'm trying to say is that collaboration is an art form, but perhaps it's actually a skill, is allowing yourself to develop that skill, because that's one of the fruitful skills.
and praise it in students, and I think it is something you can really improve on. I've become a better collaborator as the years have gone on. I don't have some innate collaborative skills. I think they're skills I've developed. And I think in science, there's this really destructive notion of the lone wolf, the scientist who sees things where others don't, then that's really appealing. And people really like either fulfilling that or pretending to be fulfilling that. And first of all, it's mostly a lie. Any modern scientist, particularly in astronomy, which is so interdisciplinary, any modern scientist that's doing it on their own is doing a crappy job, most likely. Because you need an independent set of eyes to help you do things. You need experts in the subfields that you're working on to check your work. But most importantly, it's just a bad idea. It's not, it doesn't lead to good science, and it leaves you miserable. I had some work that I was avoiding, and I thought, maybe I shouldn't pursue this scientific project because I don't care enough about the outcome, and it's going to be a lot of hard work. And I was trying to balance these two things. It's going to be really difficult, and the outcome is that maybe 10 people will cite me in the next decade because it's not. No one's asking for this question to be answered. And then I found myself working with this collaborator, Jason Dittman, and I spent a whole afternoon, hours with him working on this, and time flew by, and I just felt taller and like I could breathe better. I was happier. I was a better person when it was done. And that's because he's a great collaborator. He's just a wonderful person that brings out joy out of science that you're doing with him. And that's really the trick. You find the people that make you feel that way about the science you're doing, and you stop worrying about being the lone wolf. That's just a terrible dream that will leave you miserable, and your science will be shit.
And since I'm Russian, just murder anybody who doesn't fall into that beautiful collaborative relationship. We were talking about books.
Books, yes.
Is there books, movies?
Why was I talking about my productivity? Oh, you said you maybe don't have time for books and movies. Yes.
And you said you must make time for books and movies.
Make time to not work. Make time to not work, whatever that looks like to you. But there's plenty. When I was younger, I found a lot of kind of my scientific fulfillment in books and movies. Now, as I got older, I have plenty of that in my work, and I try to read outside my field. I read about Danny Kahneman's work instead. But when I was little, it was Contact, the book, the Carl Sagan book. I really thought I was just like Ellie, and I was going to become Ellie. I really resonated with me, that character, and the notions of life and space and the universe. Even the idea of then the movie came out, and I got to put, Jodie Foster in that, which helped. But, even the notion of if it is just us, what an awful waste of space, I find extremely useful as a concept to think, maybe we are special, but that would suck, is a really nice way of thinking of the search for life, that it's much better to not be special and have company. I got that from Carl Sagan. So that's what I always recommend.
Let me ask one other ridiculous question. We talked about the death and life cycle that is ever present in the universe until it's not, until it's supermassive, and little black holes too at the end of the universe. What do you think is the why, the meaning of it all? What do you think is the meaning of life here on Earth, and the meaning of that life that you look for, whether it's on Venus or other exoplanets?
I think there's none. I find enormous relief in the absence of meaning. I think chasing for meaning is a human desire that the universe doesn't give two shits about.
But you still enjoy...
I enjoy finding meaning in my life. I enjoy finding where the morality lies. I enjoy the complication of that desire. And I feel that is deeply human. But I don't feel that it's universal.
It's somehow absolute. Like we conjure it up. We bring it to life through our own minds, but it's not in
Exactly.
any kind of fundamental way real.
No. And the same way the sun is not to be blamed for destroying its own planets. The universe doesn't care because it has no meaning. It owes us nothing. And looking for meaning in the universe is demanding answers. Who are we? We're nothing. We don't get to demand anything, and that includes meaning. And I find it very reassuring because once there is no meaning, I don't have to find it.
Yeah. Once there's no meaning, it's a kind of freedom in a way. You sound a bit like
I'm happy about it. This isn't a depressing outlook as far as I'm concerned.
it's happiness. Yeah. So I mean, there's I don't know if you know who Sam Harris is, but he, despite the pushbacks from the entirety of the world, really argues hard that free will is an illusion. That the deterministic universe and it's all already been predetermined, and he's okay with it, and he's happy with it. That he's distinctly aware of it,
The
and that's
quantum
okay.
world will disagree with him on the deterministic nature of nature.
Well, he's not saying it's deterministic, but he's saying that the randomness doesn't help either. Like randomness does not help in the experience of feeling like you're the decider of your own actions. That he kind of is okay with being a leaf flowing on the river, like, or being the river, right? As opposed to being like a fish or something that can decide its swimming direction. He's okay just embracing the flow of life. I mean, in that same way, it kind of sounds like your conception of meaning. I mean, it just is. The universe doesn't care. It just is what it is, and we experience certain things, and some feel good and some don't. And that's life.
But I don't feel like that about life. I think life does have meaning, and it's laudable to look for that meaning in life. I just don't think you can apply that beyond life, and certainly not beyond Earth. That this notion of meaning is a human construct, and so it only applies within us and the other life forms and planet types that suffer from our intrusions or rejoice from our interactions. But it's this meaning is ours to do as we please. We've created it. We've created a need for it. And so that's our problem to solve. I don't apply it beyond us. I think we as humans have a lot of responsibilities, but they're moral responsibilities. And a lot of those responsibilities are much more easily fulfilled if you find meaning in them. So I think there's value to meaning, whether it's real or not. I just think we gain nothing from trying to anthropomorphize the entire universe. And also, that's the height of hubris. That's not for us to do.
Yeah, it also could be just like duality in quantum mechanics. It could be both, that there is meaning and then there isn't, and we're somehow depending on the observer, depending on the perspective you take on the thing.
I mean, even on Earth, that's true. But whether things have meaning or not depends a lot on who's looking.
Whether it's us humans, the aliens, or the giraffes. Clara, this was an incredible conversation. I learned so much, but I also am just inspired by the passion you have in
not finding meaning in the universe.
Right. For someone,
I'm very passionate about not finding meaning in the universe.
You're the most inspiring nihilist I've ever met. I'm just kidding. You are truly an inspiring communicator of everything from phosphine to life to quantum astrochemistry. I can't wait to see what other cool things you do in your career, in your scientific life. Thank you so much for wasting your valuable time with me today. I really appreciate it.
It was my pleasure. I'd already got my 4 hours of productivity before I got here, and so it's not a waste.
It's all downhill from there. Thank you. Thanks for listening to this conversation with Clara Sousa-Silva, and thank you to Onnit, Grammarly, Blinkist, and Indeed. Check them out in the description to support this podcast. And now, let me leave you with some words from Konstantin Tsiolkovsky. The earth is the cradle of humanity, but mankind cannot stay in the cradle forever. Thank you for listening, and hope to see you next time.